Hi everybody, this is Mrs. Hanson, and this is going to be a super awesome video, part 2 of Ms. Schneider's video about factors that affect rate. So we're going to talk about catalyst and temperature. Okay, so first of all, a catalyst, as you know, is a substance that speeds up a reaction without being consumed itself. We saw a great example of a catalyst when we had that puking pumpkin, and we added the catalyst and whoa, it just took off, right? So how does a catalyst work? Well, we're going to show you a really cool demonstration in class, but right now, catalyst somehow provides an alternate pathway for the reaction to occur. Most importantly, this pathway will have a lower activation energy. So one way a catalyst does this is it somehow puts the collisions like in the correct orientation so they happen more efficiently. Okay, so what you need to be able to do, see this energy diagram on your paper? Well, it's a classic exothermic reaction. So you have the reactants, right? And then you have the products down here. So the difference between reactants and products, like always, is delta H. So that would be the heat released. Okay, but we're talking about the activation energy. So that's from the height of the reactant level up to the hill, right? So the red line represents the activation energy for a normal reaction. If you add a catalyst, that's the green line. So I want you to take that pencil, take that pen, and draw that lower activation energy on your energy diagram. So that's what a catalyst does. So now when you measure the activation energy of a catalyzed reaction, you still go from the reactant level up to the height of the hill, but that height of the hill is shorter, okay? So now be able to explain also in sort of a short answer type way, why does adding a catalyst cause the reaction to go faster? Well, when you lower the activation energy, a greater fraction of the collisions occurring in that sample will be able to overcome a lower activation energy. So therefore, more collisions getting over that hill, faster reaction rate. Okay, so I also wanted you to see this sort of weird example, and you can maybe draw this off to the side if you want. But of course, the red line, again, is just the normal energy diagram for an exothermic reaction. But the blue line, that's just what I mean about having an alternate pathway. So that blue line this time, it's a reaction that occurs in 2 steps. Okay, but cumulatively, those 2 steps still have a lower activation energy than the original. So even for this blue line, if you wanted to calculate the activation energy for that reaction, it would be from the height of that top blue part down to the reactant level. And that would be the activation energy for the catalyzed reaction. Okay, and by the way, this is showing a catalyzed reaction for an endothermic reaction because the reactants are down low and the products are up high. All right, we will do some more examples like that in class as well. Okay, so let's see. So there's different types of catalysts. One that we want you to be familiar with is heterogeneous versus homogeneous catalysis. So heterogeneous just means that the catalyst and the reactants that are involved are in different states of matter. So this is a real famous important process called the Haber process. And basically this is how we make ammonia, which is used in fertilizers and real common. So what's going on here is the solid surface here, that's iron. So we're using an iron catalyst. And if you guys remember, you usually write the catalyst over the arrow in a chemical reaction. So you have the solid metallic surface, and then you have these gaseous reactants, so different states of matter. And what happens here is the nitrogen and the hydrogen, they get attracted to the metal. And as you can see, like by being attracted to the metal, that actually causes the N2 and the H2 bonds to break. So the N2s and H2s sort of separate. And then when the other guy comes flying through and a collision occurs, it's really easy to make the NH3 product. So by having that metallic catalyst, it sort of weakens the bonds, which lowers the activation energy. Therefore, more collisions are effective and more collisions make the reaction rate go faster. Okay, so that's a really great example of heterogeneous catalyst. And you could probably guess that homogeneous catalyst would just be when the catalyst and the reactants are actually in the same state of matter, typically in an aqueous media. You also have lots and lots of enzymes, catalysts in your body, and those are called enzymes. So where would we be without enzymes? Hardly any of the processes that go on our body would happen at a reasonable rate if we didn't have enzymes making them happen faster. Okay, so moving on. So what I want you guys to remember about catalysis is basically being able to do these energy diagrams and show what it looks like when you add a catalyst and it lowers the activation energy. Okay, and different types of catalysis, like heterogeneous versus homogeneous catalysis. All right. So what about adding or increasing the temperature? So that's probably the most obvious way that you can increase the reaction rate. So the reason why, when you increase the temperature, of course, the particles have more energy and their collisions are more forceful. More forceful collisions mean a greater fraction of those collisions are able to overcome the activation energy, which increases the rate. So again, we're looking at the same energy diagram, okay, same red hill, but this time if you have more energy, more of those collisions can overcome the big hill, okay? So now, of course, we're going to go all AP style here. So we have this formula called the Arrhenius equation. First of all, let it be known that these are three different forms of the Arrhenius equation. They're the exact same thing. You never have to memorize the Arrhenius equation. If you ever need it, I will give you whatever form you would need. Okay, the most and probably common form that we would use is this middle form. So the Arrhenius equation basically provides a relationship between temperature and the rate law constant. Because if temperature goes up, then K is going to go up, and that's going to make the reaction go faster. So why I like this form best is because if you stare at it long enough, you will see the equation of a line. Y equals mx plus b. So again, this is a graphing thing. So if we conducted an experiment, and let's say we conducted an experiment at 3 different temperatures, low temperature, medium temperature, and high temperature, and then we watched the reaction happen, and somehow we were able to calculate the rate law constant at that low temperature, that medium temperature, and that high temperature. If we actually graphed that data, and we graphed it in a very certain way, where y equals natural log of k, so that would be on the y-axis, and x equals, if you stare at this, 1 over t, okay, that's your changing variable, that would be on the x-axis. And this is a linear relationship, so you'd have this straight line. Of course, it's a negative slope because of the negative here. And what you could do here is, by having your graphing program spit out the slope, this is probably the only experimental way you could actually calculate the activation energy for a reaction. So with that slope, if you manipulated it just a little bit, you got R, if you multiplied it by M, got rid of the negative sign, you could solve for the activation energy. So that's a real powerful tool. So it's another experiment you could do to learn more about a chemical reaction. Speaking of which, just to reiterate, R is not 0.0821 like in gas laws. It's actually energy R, which is 8.314 joules per mole per Kelvin. Temperature has to be in Kelvin. K is the rate law constant. A is something called the frequency factor, and really it's just something that's inherent to a certain reaction, and it's just a sensitivity to how the collisions have to occur. If, for instance, you could just slam two things together and, you know, it's going to be the correct orientation, it's not real sensitive to how the things collide, then it's going to have a low A value. If, on the other hand, it's like an enzyme and there's active sites and the substrate has to collide just a certain way to make the collision effective, then it's going to have a higher A value. For our purposes, I would give you that number if you needed it, or you could just pull it off the graph because it would be related to the y-intercept. So I wouldn't worry too much about that. So the real important thing here is that the Arrhenius equation is something that would be given to you. You could do some math with it and you could calculate the activation energy, or you could calculate some of these other variables, or it's a graphical tool where you could set up an experiment that if you conducted an experiment at different temps, you could calculate the K values and you could experimentally learn the activation energy. Sometimes this 2-point form is useful too, just because if I only give you 2 pieces of data, a temperature and a K value, and then another temperature and a different K value, it's another way you could easily solve EA. But again, these are all 3 different forms of the same relationship, the Arrhenius equation. And really, if you study this long enough, the real take-home message is that if you increase temperature, it will increase the reaction rate, but very significantly. In fact, if you play with these numbers a little bit, a 10-degree temperature change will typically result in doubling the reaction rate. So of all the factors we've talked about, that is very significant. Okay, well, that discusses our 2 factors. We will do all the rest of the examples in class, so don't worry a lick about it. Thank you for listening.